In engineering and functional analysis, mathematical errors often grow largest at the edges of a system. To manage this, we use a specific family of polynomials designed to act as algebraic shock absorbers. These polynomials are built to minimize the worst-case error, suddenly snapping wild fluctuations into a tightly constrained, uniform ripple. We analyze these functions within the space of continuous functions on the interval from -1 to +1. In this context, we use the uniform norm to measure success. We aren't looking at the average deviation. We are measuring the single largest vertical gap between a function and its approximation across the entire interval. Compare two approaches. The Taylor polynomial perfectly matches the center, but deviates sharply at the boundaries, called Runge's phenomenon. The Chebyshev approximation hugs the function edge to edge. This illustrates the minimax objective, distributing error to ensure the maximum possible deviation is as small as possible. Managing error across an entire interval requires moving past local approximations at a single point in favor of a global strategy. The core problem is this. We want to approximate the function x of t equals t to the n on the interval from -1 to 1, using a polynomial of a lower degree, at most n-1. We can define the error function z as the difference between the two. Since our approximation has a lower degree, the highest term in the error function remains t to the n. This makes z a monic polynomial of degree n, meaning its leading coefficient is 1. The objective is now to find the specific monic polynomial of degree n that deviates the least from 0. According to Lemma 6.4.2, an approximation is optimal if its error function possesses exactly n+1 alternating extremal points, peaks and valleys that hit the maximum deviation bound. To prove this, assume a hypothetical second polynomial exists that is more accurate, meaning its maximum error never reaches those alternating peaks. If we subtract this flatter curve from our original error, the difference is forced to retain the same alternating signs at those n+1 points. To alternate between these positive and negative values, a continuous function must cross the 0 line at least n times. But this difference is a polynomial of degree n-1. It cannot possess n roots unless it is 0. This confirms our original approximation was already the unique optimal choice. This specific alternating error pattern is the mathematical indicator that an approximation has reached its most efficient distribution. To build a polynomial that hits these alternating peaks exactly, we need a function that oscillates predictably between fixed bounds. Trigonometry is the most direct tool for this. By using the substitution t equals cosine theta, we can map periodic oscillation onto our algebraic interval. This dual-axis chart maps the wave cosine of n theta as it oscillates between -1 and 1. As the angle theta moves from 0 to pi, the values project down onto our interval, drawing the polynomial t sub n of t. We can prove this trigonometric composition is a true algebraic polynomial using the product-to-sum identity. By replacing the cosine theta terms with the variable t, the periodic motion becomes an algebraic expression. This yields the recurrence relation t sub n+1 of t equals 2t times t sub n of t minus t sub n-1 of t. We generate the family of these polynomials from two base cases. t0 is 1 and t1 is t. Following the recurrence, t2 becomes 2t squared minus 1, and t3 is 4t cubed minus 3t. When plotted, these functions remain bounded between -1 and 1 across the entire interval. Notably, their leading coefficients grow as 2 to the power of n-1. By utilizing the properties of trigonometry, we have constructed algebraic functions with perfectly controlled oscillation. Theorem 6.4.3 synthesizes these results to solve our monic polynomial problem. To satisfy our requirement for a monic polynomial, we take t sub n and divide it by its leading coefficient, 2 to the n-1. Dividing by that coefficient shrinks the vertical range of the function. This normalized polynomial now has a maximum deviation from 0 of exactly 1 over 2 to the n-1. Because it hits these deviation bounds n+1 times, it satisfies the alternating requirement. This makes it the best possible uniform approximation. These polynomials have several useful traits. T sub n will always have n real, simple roots located at specific points within the interval. They also alternate parity, switching between even and odd functions as the degree increases. Furthermore, they are orthogonal with respect to a specific weight function, which is critical for applications in Hilbert spaces. This theorem establishes a precise bound on how closely any polynomial of degree n can approximate the zero line across a fixed interval. Beyond the algebra, there is a geometric reason why these polynomials are able to stabilize the boundaries of the interval. Consider a unit semicircle placed over our interval. Points marked at regular intervals along the arc are projected down onto the x-axis, determining the Chebyshev roots. Unlike evenly spaced roots, this circular projection densely clusters them near the boundaries. This clustering near the edges acts as a constraint, preventing the polynomial from oscillating wildly as it approaches the boundaries of the domain. The equi-oscillation seen in the error function is a direct reflection of this circular root distribution. This strategy for distributing error is a standard tool in modern computational science. In numerical analysis, choosing these roots as interpolation nodes is a primary method for suppressing Runge's phenomenon and ensuring stable data fitting. They are used in spectral methods to solve differential equations, where high accuracy at the boundaries is a requirement for a valid solution. In electronics, Chebyshev filters use this equal ripple property to create steep cutoffs between frequencies. Taylor approximations focus on a single point, while Chebyshev approximations use root clustering to optimize the entire domain. The Chebyshev approach intentionally sacrifices a perfect match at the center, guaranteeing the error remains bounded and stable at every other point. These functions demonstrate how mapping periodic stability onto algebraic spaces defines the practical limits of mathematical approximation.